In this lab, we more accurately represent and calculate the magnitude of charge on a piece of charge tape. As opposed to our last lab, in this lab, we do not consider the charge of the tape as a point, but rather evenly distributed throughout the tape. This lab includes similar physical principles as the last lab. It includes Coulomb's law, which represents the electric field experienced by an object in the vicinity of another charged object. It also includes the properties of charged objects, specifically that like charges attract and opposite charges repel. Finally, this lab includes the principle of superposition, which states that the total electric field experienced by an object is the sum of the electric field created by every other charged particle affecting that object. The data collected from the experiment included the length of the tape, which was 0.20 meters, the mass of the tape, which was 0.00016 kilograms, the distance between tapes, which was 0.01905 meters, and the force of gravity on the tape, which was 0.0016 newtons. In this lab, code was used to find the overall charge on the piece of tape. In the first part of the code, the necessary constants of gravity, Coulomb's constant, the mass of the tape, and the estimated charge of the tape were written in. In the second part, the function responsible for solving Coulomb's law to calculate the electrical field of a single particle is written in so it can be used for a loop to calculate the total electric field. The next section creates a function to create lines of evenly spread spherical point charges and mass. This will be used to create the lines that represent the pieces of tape. In the next section, the previously defined function is run twice to create a top tape and a bottom tape. Then lines 97 through 107 create scales that can be used to manipulate the proportions between the different objects in the program. Finally, a for loop is created to iterate through the individual point charges effects on each particle of the top tape. Then they are added up to determine the total electrical force of the bottom tape on the top tape. The result of this, the gravitational force, and the words "all done" are printed at the bottom, in the bottom three lines. And this is what the program looks like when you run it. What if the tapes were both modeled as single point charges? If both tapes were modeled as single point charges, the magnitude of the excess charge would be smaller than the new calculated value. These estimates will differ because of the nonlinear nature of electric field strength. So as new distances are considered, the effects of those differences are amplified, changing the total value. This new calculation is more likely to be closer to the real value than the single point calculation because it more accurately represents the true distribution of charge in the tape.